Hello, welcome back. In the previous segment, we discussed this Java program. It had a bug related to race condition. So in this segment, let us fix the race condition, and then we'll verify formally using spin model checker whether the race condition is resolved actually. Okay, so I'm going to add a synchronization block to resolve the race condition. So all I have to do is just create a lock. The lock object is an argument to the constructor, and we will just use this lock. What it means is that we just go to synchronized, okay, lock, right? That's it. This will make sure that counter value is not updated if the lock is acquired by another thread. Okay, so inc thread has a lock, and similarly, we need another one for the deck thread, right? So object, same lock, and we pass the object lock as an argument, and then similarly, here we put synchronized using the lock, and for reset, we do the same. We need a lock, public, not public, private, object lock, and we just can add an object lock. And of course, we need to assign this to the instance variable. Okay, and I put a synchronized of lock on this to make sure we don't reset if any other thread has the lock. Okay, invariant thread actually, although it's only reading the counter value, I am not adding the synchronized block because I wanted to make sure the invariant thread runs for all possible interleavings. Okay, that is the reason I do not want to add a synchronized block. If you want, you can add it, but I'm not adding it here. In general, you would have to add synchronized even if the thread is only reading a shared resource. Okay, so I'm avoiding it because I wanted to check whether the counter is always between lower bound and upper bound. That is the reason I'm not adding it here. Okay, we need to create the lock object in our test driver here, right? Because all our threads require a lock. I do like this, and I pass the lock here, and lock here. Okay, let us compile and make sure this code is compiled. Okay, well, we saw during the last segment, enabling the assertion didn't really help either. The Java runtime environment did not. Right, there is a problem here at some place, line number 55. I did not assign this dot lock equal to lock. Okay, I did here on the reset, I did here on the deck, and the inc. So now this problem should disappear. Okay, so it's running. The assertions are not failing for some reason. It could be that our program is truly correct, or it's just that none of the Java interleavings have created a scenario where assertion could fail. Okay, in any case, we'll stop here, and then I'll show you how to model check this design using spin. So all I have to do is I use this new construct called atomic. Okay, atomic means the whole thing here in the block will run as one statement. Okay, which is what we need for the scenario, right? The race condition happened because what the scenario was, the if statement was true here, but in the meantime, the reset thread executed and reset the value of n to be 0 when n becomes the upper bound, and then decrement thread went ahead and decremented it. That is the reason why we got into race condition. And by declaring a block as atomic, we are making sure that there is no interleaving happening until the end of all the statements over here. Okay, so now we can check whether the invariant is still true. Let us do this using spin. I will use the 651 version, and I will just analyze, okay, and generate code called pan.c as we discussed during the last segment. And now we can check whether there is any assertion violation. And you can see here, there is no assertion violation. In the previous version, we saw an assertion violation as right away at the very first line or so. Okay, so this is how you could resolve the race condition using a synchronized block. Further, we can use spin or anything equivalent to verify the design. Of course, you need to make sure your model is a reflection of the reality, which is the code, but that is something we are making assumption here. In any case, we make the synchronization block with the help of atomic in spin, And we can now check all possible interleavings. That's basically what we did. And this assertion is always true. That's all. Thank you very much for your attention.